Hey everyone, and welcome to our seventh video in the set of lectures on D-block chemistry. And today we're going to be talking about something called hard and soft acids and bases, and looking at how these sort of dictate the reactivity and the stability of certain compounds that get made in the D-block. And it's a really important concept. So it's only a short video, but yeah, I think it does deserve one on its own, so you know why certain complexes get made with some metals, but not with others. So we'll start with this nice example I've taken from the textbook actually, which kind of sets the scene and gives you a good idea of why we need to talk about hard and soft acids and bases. So it says that titanium 4+ cations form strong interactions with ligands that have oxygen donor atoms, so things like the methoxide anion and water, but only weak interactions with triphenylphosphine and dimethyl sulfide ligands. Platinum 2+, on the other hand, forms really strong bonds with the triphenylphosphine and dimethyl sulfide, but only weak bonds with water and methoxide and other sort of ligands with oxygen donor atoms. And yeah, why does this happen? Why do some metals prefer to form bonds or form stronger bonds with certain ligands, and yeah, other metals will form stronger bonds with a different set of ligands? And this is where hard and soft acids and bases come into it. And this, indeed dictates which metals like to form bonds with which ligands, and vice versa. Now to start, I need to clarify what we're talking about with hard and soft acids and bases and give some definitions. So when we're talking about acids and bases, we're not talking about like HCl and nitric acid, sort of the Bronsted-Lowry acids and bases that we usually think about. We're talking about Lewis acids and bases, which we actually said in the first video when we were describing what coordination compounds are. And in this case, the ligands are Lewis acids because, the ligands are Lewis bases. They've got lone pairs that they can donate. And the metal centers are Lewis acids. So they've got empty orbitals. They can accept lone pairs and electron pairs. So these are the acids and bases we're talking about. They're Lewis acids and bases, and the metal center is the acid and the ligand is the base. Now, hard and soft doesn't actually correspond to strong and weak. And I've got examples down the bottom there actually, so let's look at them first. So when we're talking about bases and strong and weak, we could say that the hydroxide anion is a stronger base than water, but when we're talking about this, they're both hard bases. And likewise, magnesium 2+ cation is a stronger acid than sodium 1+ cation, but they're both hard acids, even though these aren't transition metals, so we're not actually going to come across them. But it's just an example. Like, we're not talking about strong and weak. What hard and soft actually mean is weakly and strongly polarizable, or polarizing, depending on whether we're talking about the acid or the base. So now we've got hard and soft. So the polarizing and polarizable, I'll just quickly summarize actually. You'll remember we talked about it a lot with the solid structures when we were looking at small highly charged cations are really polarizing, so they can distort an electron cloud, and large anions are really polarizable, like their outer electron's quite far away, and that electron cloud can be really easily manipulated by something like a small highly charged cation. So that's what we're talking about when we're talking about hard and soft and acids and bases. And in general, like how it works, how they go together, is that hard acids prefer to form bonds with hard bases, and soft acids prefer to form bonds with soft bases. So it's hard and soft go together. So let's put that together into looking at what some hard metals will be and what sort of ligands they'll like to go with first, and then do the same for soft. So I was saying that it's hard relates to either strongly polarizing or strongly polarizable. So in the case of metals, it's strongly polarizing is a hard metal. So this is something with a high charge or a high charge density. So for example, we've got here titanium 4+, which was in that example in the first slide, Fe 3+. So you can see they've got a high charge, and these are from the first row of the transition metals. So they're going to be the smallest metals that there are. So they've got a high charge and a high charge density, and these prefer hard bases, which are ligands that are small and have electronegative donor atoms. So things like ammonia, the oxide anion, hydroxide anion, fluoride anion. So yeah, these small ligands that quite often are anionic, or in the case of ammonia, it's neutral, but it's got like a pretty electronegative donor atom. So this is a hard ligand or a hard base. And when these two come together, they've got quite an ionic character to the bonding. So yeah, you've got kind of 2-point charges. The metal is a small, really highly positively charged point, and then the ligands are also small, quite highly charged in some cases, or at least electronegative. And where they're so small, their electrons aren't going to be influenced or polarized. So they're like more point charges, and that's why it's got this really ionic character. If we look at the soft metals, and therefore with the soft bases as well, soft acid, soft base interactions, soft metals are completely the opposite. They carry a low charge or a low charge density. So the examples we've got here are copper 1+ and gold 1+. So you can already see that the charge of the cation is much smaller. Here we were looking at 4 and 3+. Here it's just a 1+ cation. It's a low charge density as well. So you'll remember that when we go across the first row of the transition metals, towards the end, the atomic radius actually increases again. So copper is, as first row transition metals go, quite a large one. And gold, where we've gone down the group as well, gold's one of the biggest transition metals. So this time, it's a large metal, hasn't got a very high charge at all. So it's low charge density, and therefore it isn't very polarizing. And these actually prefer ligands that are larger and more polarizable. So this is things like the iodide anion. So like the fluoride, it still has a negative charge, but the fluoride anion is really small because it's at the top of the halogens. Iodide's really big because it's about four periods further down. The thiocyanide anion as well, a really relatively large one, a CO. The other thing you'll notice with these, in contrast to the hard bases, is that they've got relatively, not electropositive, but not strongly electronegative donor atoms. So here we're looking at like N's, O's, F's. Here it's like I, S, C. These aren't exactly electronegative donor atoms. So where these are larger and more polarizable donor atoms that aren't so electronegative, you end up with a more covalent character to the bond. Exactly like sulfur is, well, especially carbon as well. They're not very electronegative, so they're not really holding on to their electrons too tight. So they'll have a more covalent nature. The electrons will be more between the metal and the ligand. So this is really important to know what hard metals and hard bases are, and soft metals and soft bases, because then you'll know what will bond with what. And then finally, I've got this example here. This is also in the textbook, I believe. This table of what some hard, intermediate, and soft acids and bases are. So you can see here we've got the hard ones for bases or ligands are all super electronegative things, O's, N's, or the high halogen donor atoms, whereas the metals have really high charges, 2, 3, 4, really small metals. Intermediate, so you can see, like for an example, iron 3+ is hard, but when it's 2+, it's only intermediate because it's less highly charged. And then soft, 1 or 2+ cations further down the periodic table as well. So we're going down the triads now. Things like palladium, gold, they're further down in their triads. And then soft ligands again, phosphorus or sulfur donor atoms, even hydrogen. So it's really important to be able to work out, or at least have an idea of what's hard, what's soft, and if you want, what's intermediate. And then remember that it goes from ionic to covalent as you go from harder to softer. And one thing to help you remember this is that the most common ions formed by the first row transition metals, they become softer as we go from left to right, so across the period. And if you think on the oxidation states, the trends I showed in, I think it was the second video for that one, we said that for the first 4 metals, their maximum oxidation state was quite easy to achieve. So that's why these are harder. And then as we go across, they generally only make like 2+, at a push. The 3+ is unstable. So that's why as we're going across the first row, they'll just generally become softer and softer. So this is why certain metals form bonds with certain ligands and others don't. Yeah, so it's good to know and make sure you can work out what's hard and what's soft.